for the ether, the next thing is how to prepare the ethers. This is regarding the names. Okay, how to name them. This is not how to name them, how to prepare them. So the next point is preparation of ether. So any idea how do you prepare ethers? Which is the best method to prepare ethers?
Sir, remove water,
By
adding H2SO4.
yeah, it is somewhat close to that. Adding H2SO4 to whom? Actually, ethers have two alkyl group on the either side of the oxygen, right? So what we will try to do is we will try to take an alcohol. Okay, 2 moles of it. Okay, and we need to do the dehydration. But what we need to remove the water. We need to be very careful about it. Okay, there are two temperatures. So if you take 170 degrees Celsius, right? That will lead to the dehydration of an alcohol. But dehydration, one molecule will remove one water molecule, so you will end up with ethene. This is the preparation acid catalyzed dehydration of alcohol that we have seen already. If you heat it with concentrated H2SO4, at slightly lower temperature, can you tell me what is the temperature? It is 140. Got it? You need to remember the temperature. Then also the water gets removed. But the water gets removed from two molecules. I will write them over here. And you are going to end up with an ether. So both are dehydrations. Okay. One is at higher temperature, that is elimination reaction. And the another one is the substitution reaction. Got it. The substitution reaction where the one OH is replaced by the OR group of another alcohol, so you get an ether. Got it? So this I hope is clear to you. Any doubts on this? But the mechanism we need to discuss, right? So just like we were discussing the preparation of ethers. Okay, we have just started with the ethers, right? So we were discussing the ethers, and ethers are prepared by acid catalyzed dehydration of alcohols. But alcohols can be dehydrated in two ways. At higher temperature with more vigorous conditions at 170 for ethene. These temperatures, one more thing, they are for ethene, right? Clear? And just so these are for the ethene, right? So whenever you take higher temperature for the elimination, the water gets removed from one molecule and you end up with an alkene. Got it? Is it clear, Marwa? So for ethanol, you can remember 170 and 140. If you take it at 140, two ethanol molecule will remove one H2, and this is SN1 reaction. And this is E1 reaction. Got it? So how this mechanism takes place? Let's discuss it. How do we get ethers? Okay. So first of all, we have taken H2SO4. H2SO4, as we know, is a catalyst which provides H plus. This H plus actually facilitates the breaking of OH group, right? You have an ether, you have an alcohol. Initially, we start with alcohol, and that alcohol, the OH group get protonated. Okay, and once this is protonated, it becomes an oxonium ion, and it is ready to come out. It is ready to leave. So this is known as protonation. One OH group get converted to OH2 plus by attachment of H plus, and other oxygen come and join in and removing this OH. So this is actually SN2 reaction in which this OH2 plus is being pushed out by another alcohol group. This is bimolecular mechanism, substitution nucleophilic bimolecular. So you will see that CH3, CH2, this is the left hand alcohol will get attached. I'm going to write it in this way, okay? The CH2, I'm going to write it over here because it will get connected to the oxygen. This OH now will have positive charge because it is making three bonds, and the water is this water is removed as a leaving group. It comes out. Now the last step is because this is acid catalyzed reaction. So H plus actually came in and helped the reaction to occur. H plus can be removed by HSO4 minus. So you will end up with an ether. Is it clear? But this kind of reaction is going to be used if you basically if they ask you the mechanism, then only you need to write all these steps. Okay. Otherwise, no need to write these steps. Go ahead directly with uh, with the ethers as a final product, right? So actually, this method is can be easily used for smaller alkyl groups. If you have tertiary alkyl group, that can lead to the formation of an alkene, right? Is it clear?
Yes, sir.
So this I hope is clear to you. Next is, so let me give you one another how you are going to prepare methoxymethane. Jaslene, Maro, am I audible to you? How you are going to prepare, by which alcohol, by heating which alcohol you are going to get methoxymethane. So which alcohol are we going to heat? This is quite simple. We are going to take 2 moles of CH3OH and we heat them in the presence of concentrated H2SO4. Got it? Water will be removed and you will end up with an ether. Is it clear or not? Any doubts on this? So this is the first method for the preparation of ether. The next method, there are a lot of questions being asked, and that is Williamson ether synthesis. So any idea what is Williamson ether synthesis? Jaslene, Marwa, what do we mean by Williamson ether synthesis? Okay, so what you take, suppose if you want to prepare an ether of this kind, these R groups could either be same or different. So what you will take, one group you will take as O minus. This is known as alkoxide or sodium alkoxide or potassium alkoxide you can take. Another group you can take as alkyl halide. X can be Cl, Br, I. It is better if you have Br and I, right? And you will have this ether as the final product. What is the mechanism? Mechanism is SN2. It happens by substitution reaction, right? Is it clear?
Yes, sir.
So substitution nucleophilic bimolecular. So what you take? how it happens, you take, because you have taken R or Na. Na is spectrum, that doesn't play any role, much role. Basically, you have taken O minus, and you have taken an alkyl halide, R dash Cl. These R could be same or could be different. Okay. This O minus is very reactive because it has negative charge on itself. So it will get attached to the R dash Cl, and you will end up with ROR. Got it? And the Cl minus and the Na plus will be removed. I have not written Na plus. Okay. The rate is going to be better with Br and I because they can come out easily. The bonds are weaker. Okay, this is a substitution reaction. SN2 reaction. Can any one of you tell me what should be the nature of this alkyl group? R dash. Should it be primary, secondary, or tertiary? Nature of this alkyl R dash. Is there any limit? Is there any condition?
So the primary one is more reactive.
The
The primary alcohol, like they're more reactive.
R dash should be. Your voice is very low.
Oh.
Yeah. It should be primary or it should be tertiary. It shouldn't be tertiary. Got it? Why it shouldn't be tertiary, Aisha? It can be primary, secondary. The rate actually is maximum for R dash equal to methyl. It is the most easiest, then primary, then secondary, but not for tertiary. Why? Because this is Marwa, Aisha, Jaslin. This is substitution reaction. Got it? SN2. So substitution reaction will not occur if you have branch alkyl group. Is it clear or not? So it should not be tertiary. So I will give you the example. So wherever the alkyl group should not be such that where the nucleophile cannot get attached. Is it clear to everyone? Any doubts on this? Okay. So let me take the actual examples. Okay, with the structures of R and R dash. They could be same, or if it is a symmetrical ether, we need to take the same groups. But if it is an unsymmetrical ether, we need to take the different groups. Okay. Let's say suppose if you want to prepare methoxymethane. Got it? So what alkoxide and which alkyl halide do we need to take? This is the most simplest of all. Tell me which alkoxide and which alkyl halide do we need to take? Any idea? Marwa, Aisha, Jaslin. Tell me quickly which alkyl halide and which alkoxide do we need to take? Just send it in the message as a message. Just type it and tell me. Methoxymethane, if you want to prepare, which alkoxide and which alkyl halide do I need to take? so that I can end up in methoxymethane. Any guesses? Just tell me by sending the message. Yeah, Aisha, Marwa, tell me, am I audible to everyone?
So sodium methoxide we can use.
Yes, 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 yes. Now you are audible. Sodium methoxide, CS3ONA, exactly. And very good. And alkyl halide, we can take because we need to attach methyl. Take any good alkyl halide, alkyl group with a good leaving group like bromine or iodine. You can take CSCI, which is the most easiest to break. Is it clear or no? Not.
Yes.
Okay, great. So in this case, we don't need to think about which alkyl group need to be taken with oxide, which alkyl group need to be taken with iodide. That I don't need to consider because both were same. So it was not a problem. But problem will come up if I ask you to prepare this kind of it. Okay. There are a lot of names to it. Common name is methyl tertiary butyl ether. Now IUPAC name is 2-methoxy 2-methyl propane, because this is the parent chain. Okay, the longest continuous carbon chain. I need to number it from one end to another. And on the second carbon, I have methyl and methoxy. And that's how I'm going to write the name of this compound. Okay. Next is how I'm going to choose which alkyl halide and which alkoxide I need to take. So let me write both the options. The options can be, we can think of the options by choosing the bonds. Okay, I made this demarcation just to show you that you can take alkyl halide this one and alkoxide this one. This is one of the options we can have. So let me write them. I have taken this as alkoxide and the other smaller alkyl group as the alkyl halide. This could be one of the options. What could be the other option? Aisha, Marwa, Jasleen, tell me.
So
What could be?
sodium methoxide.
Sodium. Yes, exactly. Sodium, potassium, they are just the same thing. And yes, exactly true. Which alkyl halide? That tertiary butyl I can take. Is it clear or not? Got it? Br or I. Anything will do. But are both the options permissible or just any one of the option is allowed?
So here, the it's a tertiary alcohol, right? I mean, a tertiary halide.
Yeah, tertiary halide, exactly. Yes,
So it will undergo elimination.
exactly. The tertiary halide, you know that there is no SN2 reaction that can happen on it. Hmm. Right, that cannot happen. So this option is closed. It will give us some different product. Elimination will happen. Got it? So this is obviously this is not the suitable option. Right, Marwa? Jasleen? This is not the suitable option. But then why this option is suitable? Any idea? Why should I say that this option is more suitable? The first option to get the about desired ether. It can happen most easily. Why? Because this is a smaller group and can easily undergo the reaction. Is it clear or not? Got it? Any
Yes, sir.
doubts on this? Yeah. Marwa, Jasleen, I hope this is clear to all of you, right?
Yes, sir.
Okay. So this you need to, this is a very common question for all levels, you will find them. Okay. Let me give you some other examples of it. Let's say if I want to get this ether and I will give you two options. You need to tell me which is more appropriate or which is uh, absolutely impossible. Okay. So or both are possible? So, Jasleen, what about the first option? This first option. Can it occur easily or not? What do you think? This is O minus and Na plus. How can we get the ether? How are we getting the ether? Just look at it. What should happen so that we can get the desired ether? pH is that benzene, phenyl, right? So it should happen in this way. Clear? And the Br must get removed, right? But is it going to happen easily, or will there be any difficulty in happening? What do you feel? Is it the right method? If it can happen easily with a good rate, it is the right method to prepare the methoxybenzene. Whose common name is Anderson. So this is the right way. It can happen very easily, right? Why? Because it is a very small group and it can easily undergo the reaction. But what about second one? Can that also be used? Aisha, Jasleen, Marwa, tell me. Can the second option be also be used to get the desired ether?
So because it is aromatic and it has very strong bonds, so it
Mm-hmm.
will not be able to break.
Exactly. Got it. So it is not going to react. Okay. This substitution is not going to happen, and this reaction is not going to happen. So in this case, the first step is the appropriate method to prepare anisole, because that is where the SN2 reaction can happen most easily. Okay. Is it clear? So let's do some conversion problems, right? For the ether. And not only for the ether, from the previous chapter also. If you want to replace, you need a very high temperature. Okay. That also we have seen earlier. So what is the structure of A, B, and C? I hope everybody can see the question.
Yes.
So these are the reactions from both the chapters of haloalkane, haloarine, and our current chapter of alcohol in it. So what is the structure of A? Tell me.
So chlorobenzene.
Yes, this is chlorobenzene exactly. And what is the structure of B?
Alcohol.
Yeah, phenol, right? This is actually, suppose if you don't take H plus, it will remain as O minus Na plus. Okay. Normally, to prepare phenol, that is bimolecular nucleophilic aromatic substitution. Got it? Marwa, is it clear? So you have this. And if you have taken ethyl bromide, then the sodium phenoxide is going to attack on the ethyl group, removing the Br, and you will end up with CH3, CH2O. Got it? This is the SN2 reaction happened on this. Is it clear or not? This is ethoxybenzene being formed as a product. Got it? Clear?
Yes.
Very simple. Just you need to be Br minus and CH2 plus. You can think in this way also. Br is electronegative and this is O minus. So attach the minus to the plus charge. That's how you can get the final answer, right? So this I hope is clear to you. Okay. So let me move on to the next one. Next step is next question. Regarding the preparation of ethers from the first, from this, and actually this is uh, related to both the chapters. Okay, so don't think that this is from the alcohol chapter. So you need to tell me all these structures or the formula. So what are P and Q?
So CH3, CH2, O, and A,
Yes, this
and
is the
hydrogen gas.
test for alcohols. Okay, alcohols liberate hydrogen gas with ether, right? Uh, alcohols, the hydrogen is replaced by sodium, right? Which is an electropositive element. So absolutely correct. CH3, CH2, ONA, right? And this gas is hydrogen, right? So this is a test to differentiate alcohols from ether. Ether will not liberate H2 gas. Phenol will also liberate. Okay, this. So phenol and normal alcohol cannot be identified using sodium, but alcohol and ethers can be identified using sodium. Okay, now this is P and Q, right? And what should be R so that you end up with this compound? What should be R? Something which can replace OH by R.
So bromine.
Yeah, bromine, some compound of bromine.
Mm.
Got it?
Phosphorus tribromide.
Yeah, for red phosphorescent, yeah. Got it? So I hope you are able to recall. Marwa, were you able to recall this? This we have studied in the previous chapter. Justine, PPR3. We have seen various methods which can convert the alcohol to alkali lines. Right? This was one of them. So now you reacted with P. This compound, this bromide, you reacted with P. Clear? So what we are having, once you reacted with P, this is O minus. What will happen? Aisha, Marwa, tell me quickly. Jasleen, this is minus, and what will happen? Yes, you can tell me quickly. Very easy question.
So the Williamson synthesis.
Yeah, Williamson ether synthesis. Exactly. So we are going to end up with no Jasleen. This is minus, this is plus, okay? And Br is minus and CH2 is plus, right? So remove this as a salt, right? And connect the remaining two groups. SN2 reaction. Is it clear? Jocelyn and NaBr. Williamson ether synthesis, okay? Alkoxide and alkyl halide, you are going to end up with ether, okay? Be careful that the reaction happened without any steric hindrance, or bulky group should not be there, right? Next question. This is from the alcohol chapter, the first method which we have seen for the preparation of alcohol. Got it? So very similar reaction, just slight changes I have made. What is option A? And which reaction is this? Tell me quickly. What is this option A? Dilute H2SO4 or addition of water, or we can call it as acid catalyzed hydration of alkanes. Yeah, Marwa, any idea? Tell me quickly. We have already seen it. What is the IUPAC name of A? Yes. Jaslin, what is A? Aisha, what is A? Dilute H2SO4, addition of water. We have seen it.
So the double bond breaks, I remember that.
Yes, exactly. You are moving in the right direction, absolutely in the right direction. This is addition of water. Got it? Acid catalyzed hydration of alcohol. Markovnikov addition, right? Where the H plus get attached to the carbon atom bearing more hydrogens, and this is OH. Got it? Is it clear or not? So A is okay. This is an alcohol. As at the first method which we discussed. Arva, is it clear? Just clean. And Aisha, now I hope you can recall. Got it? Then I reacted to the Na. So this reaction also I can make out very easily. This is a test for alcohols. And then we reacted with CH3. Got it? So this is SN2 reaction, so you end up with this is Williamson ether synthesis. Is it clear or not? All of you tell me quickly. Very
Yes,
basic
sir.
and important question, right? Okay. So let's move to the physical and chemical properties of ethers. So basically, they are polar molecule. They have some plus and minus charges, but not in large amount. Oxygen is electronegative, so it will have a negative charge, and the alkyl group will have a slightly positive charge. Okay. So they are actually very weakly polar. The polarity is not as high as that of water, and because of their less amount of charges, they exhibit the lower boiling point. So they have lower boiling point than the alcohols with the same molar mass. Clear? But their boiling point is higher than the alkanes. So suppose if we take a butane, if we take a butanol, and if we take ether of 4 carbonate, what is the order of boiling point? Tell me quickly. The first one is an alkane. The second one is the alcohol, and the third one is ether. What's common among the three? The common thing is that both have 4 carbon atoms. Got it? Is it clear?
Yes.
So, which one do you expect to have maximum boiling point? Boiling point will be maximum for the alcohol. Why? Marwa, Aisha, why the alcohol will have maximum boiling point?
So hydrogen bonding.
Yeah, it's
OH.
bonding. Yeah, exactly. Hydrogen bonding is stronger bonding because OH has H plus and O minus, so they are going to attract each other. Right? So normally this is having the highest boiling point, followed by ether, and then you have the alkane, which is almost non-polar. Okay, so boiling point will be maximum for alcohol. Then you have it for the ether, and then the alkane. Is it clear? So boiling points, same carbon atom, the alcohols have larger boiling point, but the water still will have more boiling point. Okay, in many cases, for as compared to small alcohol, because water there are more number of hydrogen bonds. Okay, so let's talk about the water solubility. So ethers are up to some extent they are like alcohols, but they are not like alcohols. Both the things are there. They have oxygen like alcohols, but there is a OH group. Okay. So how can we compare their solubility in water? Same thing we are going to apply here also. Whatever we have applied above, the same thing we are going to apply here also. Yes. Which is going to be more water soluble? Will it be alcohol or will it be ether?
So
Which can be
alcohol.
yeah, alcohol. Why?
Because they can form hydrogen bonds.
Yes, exactly. So hydrogen bond because they have OH. There is a very there is a saying that like dissolves like. Okay, so if you have a same type of groups, that compound will be soluble. Those two compound with the same type of functional groups can will have same type of intermolecular forces and they will get dissolved into each other very easily. So alcohols are more soluble than ether, but overall solubility can that depends upon the nature of the alkyl group. If the alkyl groups are larger, both will be less soluble. Okay. Boiling point is, as I already told you, if you have same carbon atoms, alcohol will have larger boiling point than the ethers with same carbon atom. Now the reactions. Okay. So ethers actually can react. They have oxygen linkage and they can break. their oxygen linkage, but that is happening in the acidic medium. So if you react with them with acid, you are going to end up with ROH and RX. This is just the reverse of your Williamson ether synthesis. If you look at it, Williamson was just the reverse. Can you observe it? That it is just the reverse of Williamson. Williamson, actually, we were trying to combine the alkoxide ion and the alkyl halide. This is just the reverse of it. Okay. So let me ask you something. Let's take specific examples of the ethers. So how it is going to break? And what will be the products?
So CH3I and then we get alcohol.
Yes.
CH3, CH2.
Yeah, CH3I, exactly. And CH3OH. Absolutely correct answer. And what's the mechanism here? The mechanism here is first you took H plus. So I will protonate this oxygen with the H plus. Like this. And then this, whatever the halogen is there, then this halogen may combine with the alkyl group to give us an alkyl halide and an alcohol. Got it? This is how it can happen. Clear?
Yes.
So, but in this case, there are not much variables. Why? The variables are not there because both the alkyl groups are same. Got it? Both alkyl groups are methyl. So there is not much tension of where to put the alkyl iodide and where to put the OH. So this is not the problem here. The problem is going to come up when you have different set of alkyl. Got it? That is going to be a problem. Or where to connect the iodide, where to put the OH. Okay, if you have different alkyl, so that also we will see. As of now, we can think of, but what will happen? Let's continue with this symmetrical ether only. Let's see what will happen if you have if you took 2 moles of HI. 2 moles. So I took 2 moles of HI. What is going to happen over here? So first react the HI, both the HI one by one. Okay. So with a 1 mole, the products are already written CH3OH and CH3I. Okay. Now, if we react with one more mole of HI, who is going to react with that one next with the next mole of HI? Who is going to react? Yeah, Jasleen, Marwa, Aisha, tell me. With the second mole of HI. The first mole, the answer is already written.
So CH3I and water. Two moles.
Yes, the CH3OH is going to react, right? Yes. This is going to end up with C. This is also going to end up with CH3I, and this is CH3I. That was already CH3I, right? And water. Got it. So if you have a symmetrical ether, you don't have to worry at all. And if you have uh, as 2 moles of HI, then also both places you can put the I group in the aliphatic ethers. That you can understand, right? So I hope this is clear to you. Got it? Okay. Next is what happens if you have different set of alkyl groups. That is the problem. With 1 mole of HI. With 2 moles, again, it is not a problem because with 2 moles you can put I on both the groups. Okay, with 1 mole, my problem is over here is should I put I with the CH3 or with the ethyl? So what should be the answer? Yeah, Jasleen, Aisha, Marwa, tell me. Which one do you think would be the right answer? Tell me.
The first one.
First one, why? Yes, correct. Absolutely correct. Why? But what do you think? With 2 moles, okay, that will not matter because both will turn to iodide.
Because it follows SN2 mechanism.
Yes, SN2 mechanism. Exactly. So what you have this oxonium ion first. The mechanism is first you the H plus get connected to both the alkyl groups, right? The oxygen of both the alkyl. This is known as oxonium ion. Okay, and then the I minus will attack on any of the alkyl group. So it will be easier to attack on the smaller alkyl group because of the SN2 reaction. Okay, if the I minus is attaching itself on the CH3, this group should come out. You are going to end up with CH3I and OH CH2 CH3. Clear? So this I hope is clear to you, right? This is SN2 reaction. But will it always be SN2? Or it can be SN1 also. Any doubts in this? This is SN2. If it is smaller alkyl group, it can be SN1 if it can form a stable carbocation. Are you getting my point? If any of the alkyl group can form a stable carbocation, is it clear? With the tertiary alkyl, the mechanism
Sir, can
is.
we
Hmm.
use
Pardon?
benzene? Can we use benzene like as
Yes, yes.
well?
Yeah,
Benzene.
I'm coming to that benzene also, methoxybenzene, anisole. Yeah, I'm coming to that. First, because I've written this statement, so let's continue with this. Methyl tertiary butyl ether. Got it? So first, we are going to form the oxonium ion. Then break this oxonium ion. Will it break on its own? Will it break by a cation, or will it break by attachment of I minus? How it is going to break? Got it? So how it is going to break? You can see the alkyl groups. One is methyl, another is tertiary butyl. This tertiary butyl group is tertiary. Okay, this is 3 degree, and we know that the cation stability of cations are very. The 3 degree cations are very stable because of the inductive effect. Okay, because of the branching, because of the hyperconjugation. So what will happen? This will break from this side, and and the mechanism will also be different. It's not SN2. That was with smaller alkyl groups. This is with larger one. Got it? Deslin, Aisha, Marwa. Is it clear
Yes, sir.
up to
Yes,
this
sir.
point? So now where I should put the I minus? I minus I'm going to put on the cation. So in this case, I put it on the more branched alkyl group. But that will only happen if it is SN1, and that will only happen if it is one of the alkyl group is tertiary, then it can form easily. Okay, and CH3OH. Let's talk about phenyl group. Okay, but this I hope is clear. So if normally with a smaller alkyl group, I is going to you are going to choose to put the I on the smaller alkyl group, right? Methyl. Okay. But if there are two groups, one is tertiary, then you are going to put the I on the tertiary. Got it? Is it clear or not? Now let's discuss what will happen if you have an aromatic ether. Okay, there are few things which need to be answered in this. The first and the foremost thing is which option should be the right answer? The above one or the bottom one? Which one should be the right one? Or both can form easily with equal ease?
The phenol one, the phenol and ethyl
Yeah,
alcohol.
phenol and CH3 ion. Yes, yes, Jaslin. But what is the reason? This is not going to happen. So what's the reason? The reason is the general reason which we see when we actually react the aromatic halides. Hmm. So what's the reason? The reason is, can anyone now tell me? Yes. It is SN2, but there is one more thing. This bond you're not never going to break. Why? That is true. That is SN2. Absolutely correct. But one more additional information which we need to add on here is that this bond you will not break. You will break only this one. What's the reason? The reason is quite clear. Okay, because of the partial double bond character due to resonance. Got it? Is it clear? And this is SN2 mechanism that is also need to be told along with what I said. What I said will be uh, will be realized more when you react with 2 moles of HI. The above reaction was with 1 mole of HI. Okay. With 2 moles of HI, what are we going to get? Now you will appreciate the explanation which I give. Okay, that whatever the explanation which I give now, that is playing a key role in deciding the answer to this problem. HI normally, if you take 2 mole, what happens? Both the alkyl groups have I connected to them. Is it clear? But now what is going to happen? What will happen? So you will have first let's add first mole that we already know. Let's do them one by one. Okay, HI. This was SN2. Yes, that was absolutely correct. Now I need to have reaction one more time with 1 more mole of HI. Okay, what will be the product? Now the situation is you are more close to the answer, but there is a small thing which you need to keep in mind. So just tell me quickly.
So we get phenol and with CH3I.
Yes, exactly. There is no change in the answer. Why? Even with 2 moles of HI, the same phenol has not reacted further with HI. Why? What's the reason?
The partial double bond
Partial
character.
double bond character. So
Okay.
it is not. It will not be possible for us to remove that OH group. Okay, that phenol will not react. So this thing we can try to correlate with the alkyl halide chapter also. Haloalkane, haloalkene. There, all the methods which were used to convert the OH to halogen were applicable on the aliphatic alcohol, they were not applicable on the phenols. Is it clear or not? Okay. So, next thing is reactions of we have seen one of the reaction, and the root cause for the that reaction was that partial double bond character due to resonance. So let me show you what are the resonance structures. Got it? So these are the resonance structures you can see over here. And these resonance structures, which shows the movement of the lone pair of the electrons. Okay. Can help you to understand that why the carbon of benzene and oxygen bond has the partial double bond character. Is it clear or not? So this minus charge come into the benzene at the ortho position. It pushes the negative charge further at the para position and so on. So this is how the resonance of the anisole is going to occur. One more thing which we realize over here is that there are the ortho and the para positions which become more electron rich. Got it? Those are the positions where the electron density is increased by large amount. Is it clear? You can see those are the positions from where the negative charge is passing. Got it?
Yes, sir.
Is it clear or not? So now if we do any reaction, okay, of benzene related to the benzene, the above reaction was related to the ether, HI. Now we need to know that if we do any reaction related to the benzene ring, that reaction is going to occur at ortho and para position. Because ortho and para positions are the positions which are having high electron density. Is it clear or not? It is having high electron density, so those are the positions which are going to be more reactive. If you, let's say, if you try to do the bromination of the benzene ring, okay, by taking Br2, in appropriate solvent, so where this Br2 is going to get attached. This Br2 is either going to attach at the ortho position or at the para. Is it clear?
Yes.
Okay. Or if you do alkylation, Friedel-Crafts alkylation, Friedel-Crafts acylation. Let's say if I took CH3, Cl and AlCl. Got it. AlCl3 will remove the Cl, make it CH3 plus. That CH3 plus, as you can make out that minus charge is at the ortho and para position. So this methylation, Friedel-Crafts alkylation is going to occur either at the ortho position or at the para. Got it? Is it clear or not?
Yes, sir.
Nitration, how we do the nitration? By taking HNO3 and H2SO4, mixed acid. And nitration actually, H2SO4 helps to remove the OH and get the NO2 plus, which is the electrophile which get attached to the benzene. That NO2 plus also will get attached to either the ortho position or the para position. Okay. It is because of the resonance of the lone pair of oxygen, which is making the ortho and para positions more electron rich. You can see by writing the resonance structure that the ortho and para positions are the one from where the negative charges pass. Is it clear? And suppose if you have a bigger group like NO2, okay, or some bigger group, so there the generally the para is more formed. It is a major product because the bigger group will face while getting attached to the ortho position, it will face repulsion from the OCH3 group. Got it? So this chapter is almost complete. We will do some problems, and next chapter we can start with coordination compounds. Right? Will that be okay with all of you? Am I audible? Aisha, Marwan?
Yes, sir.
Okay. So we can start with that reaction. So let's move and let's end this class and let's continue in the next class. Okay. Bye bye. Good night.
Thank you, sir.